current estimates are about $25,000 per kilo to the lunar surface. If we could do that. Yeah. For that reason, the cost of feeding people on a move through continuous supply is extremely expensive. Take hamburgers, french fries, and a Coke. You've got a couple of pounds, then it's $50,000, $2,005 for lunch. So, you know, what's the big deal about a lunar lunch? It's pretty expensive. Maybe go to the next. In looking at some of the early NASA projections, there's a book they put out in the mid-70s for design that would be 10,000 people. They were looking at the illumination and the requirements for agricultural systems. And you can see that they were looking at many megawatts of power for lighting and food processing the agricultural component. And obviously, in order to make space a place to work that's viable, we have to be able to develop a food supply and the ability to be as self-sustaining as possible. Go maybe to the next one. This design is taking a look at some of the lighting requirements. You can see if you go down here at the bottom of the graph that again, the plant growing energy requirements are the single biggest factor for this large-scale type of project. So the plant lighting, and not only just the lighting, but the removal of the heat associated with that is going to be a big deal on the lunar surface. The moon is not a particularly good conducting medium, and so you're going to have to spend a lot of power getting rid of your waste heat. So if you're generating a lot of lighting generates a lot of heat. It's a very energy-intensive kind of process. Now, in small applications, we'll have small, there's this SP100 power plant that should, on a small scale, be able to supply the power needs of small bases. But if you start to talk in terms of hundreds and thousands of people, then you're going to have to scale up the imported power plants that you bring, and so there's a continuing issue of cost. The alternative is trying to build power systems on the moon and use photovoltaic collectors to provide your power source. And they're good as long as the sun is shining. But if you have this tremendous need for power and you go through a 2-week dark period and you don't have the capacity to switch to an alternate backup source, then you have a potential significant design issue. Our assumption in setting up some experiments that would interest students, that we would like to engage students in, has to do with the lunar photo period and this potential issue in terms of lunar-based power supply requirements. We start with the premise of saying, well, what's the least amount of light, and try to investigate what the least amount of light would need to sustain a variety of food plants through a photo period which would have essentially unlimited power constraints during the lunar day, but potentially less power available during the 2-week lunar night. And so we're not able to find in the literature any consistent study across the wide variety of food plants that we've been able to investigate. They have essentially a vegetarian diet. This is not that hard to determine. It doesn't require a huge expensive laboratory, and to control your lighting schedule is something we felt was in the province of most classroom teachers. Our goal is basically to try and introduce some of the complexity of high-tech space-based agricultural systems to students who are in high school and college, and to engage them in different kinds of fairly inexpensive experiments that start off with the photo period research that we're talking about here. So that's the beginning rationale for LUNAX. Our National Space Society chapter in Milwaukee participated in the design contest for a lunar base for 1,000 to 3,000 people. Did the other gentleman leave with that paper? Oh, okay. You would let them copy. I don't, this is way over the top, so just let them copy the title. Maybe you could give them some note paper to do that. Our goal was as a chapter was to participate in the 1989 design conference that the National Space Society held in Chicago in 1989. And so this particular issue came up and looking at scaling up from hydroponic systems to small, 3 to 5, 12, 15 person scales. And some of the early NASA projections did show up the same kinds of figures, right, as you have intensive energy supplies. And so that basically is where we're starting to take a look at investigating a wide range of food plants. We started by convening a number of people, a couple of high school teachers in Green Bay, a college biology teacher from Hayward, Wisconsin, Dr. Gary Lake, who is a member of the Wisconsin FAST Plants program. That's the National Science Foundation education project in the University of Wisconsin in Madison. And that particular program is working especially with fast-growing brassica plants that were developed by Dr. Paul Williams there at the Department of Plant Ecology. They're very fast-growing. They were bred selectively, and they go from seed all the way through flower, complete plant cycle in 39 days. So these are very small plants, and they were initially developed to try and show the effects of genetic changes, so that you have a short time for the life cycle of the plant. You can see what your changes are without having to wait a long time. And that also makes the plants a very ideal topic for biology teaching, because you can see a result around a short order in the classroom. They're very inexpensive. Through licensing arrangements, the Fast Plants program has a technical manual. They have seed packets and supplies on a variety of brassicas. The program also has an extensive professional research arm. There's a genetics cooperative for other brassica plants. So that particular program is a major primary and secondary education initiative at the University of Wisconsin. The National Science Foundation has given them over $1 million, and so they are taking that particular range of materials throughout the country looking at brassicas. We started because they had the procedures and manuals. We had produced a series of different lighting schedules that students could use. And the second issue, above and beyond lighting, is the issue of trying to live off the land. And in order for, not only do you have to accommodate any design requirements and problems that come from limited power supplies, but there's also the question of shifting from physical chemical systems, which are highly engineered and very expensive and very heavy to lift, and to live off the land, and by using your lunar resources then to construct agricultural systems which you can expand to sustain a larger population. And what we have to work with is the lunar regolith. And you can just talk about physical chemical systems. There are lots of different kinds of closed loop. They're part of the closed ecological life support system. And many of the early ones are looking at reacting the chemicals and wastes that are produced and heating them and handling them chemically. That again is a reasonable and short-term solution for a short stay and limited number of people. But the focus primarily is on hydroponics because of their high productivity. But there are also problems with hydroponic systems. And hydroponic systems they have a continuing import requirement. They also can be tricky in the sense that solutions and chemical changes can occur rather rapidly. They're subject to monocrop infections and other types of problems. In your traditional soil-based agriculture, is much more stable. It has larger buffering capacities in terms of the chemical changes that might occur. It also is highly diversified in terms of the microbiology, so the stability of the soil-based system certainly is superior to an artificial system. The productivity, however, is much, much less in terms of some of the engineered applications. Out of the University of Utah, Dr. Salisbury has produced some experiments on closed system growth of wheat, and the productivity is several 100% for those systems over what conventional yield would be under ideal conditions in the farmer's field. The risk, however, is that such systems, if you were designing or highly engineering a particular system for a particular plant, you kind of put all your eggs in one basket. And so if you have a diversified number of plants, you have to modify that, or when that, depending on what the crop is, what the requirements are, you translate that back, and that means you have to bring up X number of these modules. And so there again, you're looking at weight penalties. So the idea of using a much more traditional soil-based system, if you can, for example, get large dumb volumes and the ability to potentially use lava tubes, for example, or to use large tank structures, may give us the ability to have kind of surface area. We wouldn't have the same productivity, but we might be able to use a more traditional and more balanced and diversified kind of plant community.
The question is, how much productivity would you lose, or could you just pick something somewhere in the middle range to cover, say, 3 or 4 different plants, cereals?
Well, if you look at some of the articles that have been published, people have the crew eating, a very few different kinds of plants.
I think they got it down to 3 in one article I ran across. They picked the strangest things I've ever heard of, and nothing that's commonly grown as far as I can tell.
Well, there are 9 or 10, I think, primary plants that would supply most of a balanced human nutrition. And potatoes and soybeans and wheat, onions, tomatoes, lettuce. Those are some of the.
Yeah, but the one I saw one article that they were using, I don't know, Swiss chard or some strange thing, and they were down to 2 plants or something, and they were going to reform all this stuff. And it just didn't sound very appetizing.
We move on to the next overhead. If you're looking at some of the, pull that up just a little bit. The numbers of square meters per person are not very large if you're looking at a variety of different kinds of plants. But here again, if you have to have a separate growth module that's specialized for each species, how much weight does that translate back into? If you throw animals in the mix, and you have a lot of waste biomass. Not everything that you grow is edible, so the animals are good processors of waste biomass. You have additional requirements. This, you see varying figures for the kind of production, depending on what technology you use.
You're answering the question. See, my point was that they individualized these modules. The reason they're getting such high productivity is they forced everything to absolute optimum for one particular plant.
Exactly.
If what I'm saying is, can you make a module or whatever that would cover a range and you could adjust it just for, say, you're running the difference between soybeans and wheat? What would be the difference you would have to adjust
Sure,
it to?
I'm saying,
if
you have a garden, you do that. I mean, that's commonly done.
Yeah. But I mean, in effect, that's what you really would do. You grow all the varied varieties in different rows, one right next to the other. That's what you do in an ordinary garden. Could you build a module that would cover everything?
Figures like you get here in terms of the number of square meters per person are based on very, very high projected levels of demand, and so that doesn't throw in having a rainstorm come or hail, or it doesn't necessarily predict what type of plant pathogens may pop up and wipe out your crop. That's why the ecological stability of all this is one of the hard to quantify aspects, and that's why a soil-based and more diversified ecological balance, as opposed to just going with monocrop hydroponic systems.
You have a hard freeze in Florida, now you get in California.
Yeah. Well, it's going to be pretty expensive to get California oranges on the move, and I guess that's the whole point. So at any rate, there are significant questions about the kind of high yield and monocrop hydroponic systems as really being a reliable and practical kind of base for large populations. And if they turn out not to be stable, then our alternative is to know what we're very familiar with, and that is pretty much conventional types of horticultural practices. So what we're talking about here is really not the near term of the next 15 or 20 years of what's really in design right now, but what would happen when you have the capacity and significant infrastructure to design large enclosures and have adequate power supplies, and then using the lunar regolith as the substrate for your growth. We can go into the next. Here are some other figures on growth in yield data. And depending on who you read, you'll see a variety of precision rates of growth per day. Tomatoes, wheat, soybeans, cucumbers. I personally think that another aspect that's really important, especially with large populations, is that if you only have 8 or 9 different things to eat, that has a significant impact on morale. And so much of human culture is concerned with food. Child socialization, business is conducted over food. Food has an awful lot to do with our morale. And so I also am very skeptical that you can, in fact, really intelligently design for such a limited range of crop species.
That goes back to my earlier comment. They were picking some strange thing I'd never heard of, and I had no desire to eat, and they couldn't see how they could live it.
I think people would grow spices and little pots in there.
No, I don't think they'll grow pots, spices in the rooms. I think that's a very critical dimension of lunar agriculture, and we need to research those spice plants and their requirements just as much as we do tomatoes and wheat. They have this salad machine out at Ames, and I think they hope to get this to yield some supply of lettuce like once every 3rd day to somebody who will be about to cream it. Well, this is a learning experience, but I can just see those crew members now. Boy, I can't wait to get that extra leaf of lettuce. They'll probably be just about as enthusiastic as the Desert Storm guys were about their ready-to-eat meals. But I think these are not really minor issues, and it's very hard to engineer these kinds of things and put numbers on it and sell this to research world. I think it makes much more sense, especially as we look out 20 or 50 years, to say, hey, we basically need to have the same kind of variety as we can. I was from Wisconsin. I don't think we're going to see cows on the moon for a long, long time. I think we're going to see pretty much vegetarians up there. But I do think it makes sense to take a much broader scope of what we need to grow, what we'd be interested in growing up there. I also think that it allows people in different parts of the world, as North Americans, we're generally used to certain kinds of dietary preferences. And if we're going to build a space-faring civilization, and we're going to have people from the Philippines and Thailand and South America and Africa and different parts of the world, their food preferences and crops also need to be looked into and be part of that kind of mix. The adaptability and the ability to create designer biospheres for certain types of plants, I think, is another whole issue. I don't think there will be just one. And part of our interest in LUNAX is to introduce this range of variability to student interest and to raise the research so we can go to our next slide. In looking at the Apollo samples, you can see the different kinds of materials that the lunar basalts are comprised of. And one of the things that we are looking at as a research area is a lunar simulant. Dr. Paul Weidman at the University of Minnesota Space Science Center has taken these basalt rocks, which are about 1.2 billion years old. And these rocks are very similar in terms of the geology to the lunar Mare basalts, in that they overlie some orthositic base rock, part of the mid-continent rift. And in fact, what he has done is to create a simulant that is very similar in chemical composition to the Apollo 11, to one of the Apollo 11 samples. And what he does is he takes There's enough few of you, if you're interested in looking at this stuff. He takes this rock and ships it and breaks it up, and the Mineral Resources Lab at the University of Minnesota is where they did the initial work on taconite processing. And so they grind up these base rocks that illustrated, and they you want to flip to the next chart here. The regolith has lots of glassy material and it's very fine particles. And so you can see when the ejected blankets are thrown out of the craters, a lot of that is open because of the impact. That forms a lot of the molten material. Basically, remains as a glassy substance and forms these spheres just like a drop of water. And that's what they look like in small scale. That glassy material also fuses with some of the remaining pulverized rock and forms what are known as glassy agglomerates. So you have basically rock and then you have this melted material in a range of particle sizes that you can mixed. So there's a wide variety of different grain sizes, and that's what they have tried to mimic in producing the simulant. And if you want to pass this around, the materials here are produced in a 6,000 degree plasma furnace. And the ground up particles of rock are dropped through this high temperature plasma, and then they fall. This is up on about a 3-story scaffolding in the resources lab. Those rock particles melt almost instantly as they drop through the plasma, and they form droplets, and then they fall into a container. And like the fast you can open that and you'll see what it looks like. It's very black-looking material. And this one, or this particular bag, is primarily glassy material. You just pass those around.
It's the base salt.
So all of this, everything that I'm showing you here is based on basalt rock. There are two components in those. There are several components in the lunar soils. There's a north acidic rock, and there's basalt, and then there are glassy agglutinates. And the glassy agglutinates are really from both sorts, coming from the impact of the meteors. If you're going to characterize a lunar regular type of soil, you're going to have rock and you're going to have glassy components. The glassy components comprise anywhere from 10 to 30% of the amount of the soils. And here's just I think that's also.
Was this the same stuff?
Yeah, that was the glass. If you compare the colors, here's the base rock, and this is much more gray color. Dr. Wyland said that if you just grind up gray rock in those fragments, it's a much lighter color. I believe we talked to Dr. Schmidt, and Dr. Schmidt looked at the processed rock that had gone through the plasma furnace, which is all black, and he said that's what the moon looks like. So by chemical composition, by grain size, and also looking at the glassy agglutinates, he is able to create a much less expensive analog for a variety of different research purposes than trying to get hollow samples to do anyway. But it costs a lot less than $30 billion to try and work with a lunar simulant. And this material that you're seeing here has had very little agricultural work done on it. If you take a look, for example, at the biosphere, they're looking at trying to create a large enclosure with a variety of different species in a complex ecology, and that's their primary interest. But they have not really, used the assumption of trying to live off lunar resources. What they did was simply take the soils from around the watering holes of the cattle ranch that they bought, and so they basically, their soil bases there in Biosphere 2 are basically cattle manure, sitting out and baking in the sun for a long time. Yeah, and this particular material will grow plants. especially with different kinds of amendments. And it does, yes.
You mentioned earlier about the unused portions of the plants, you know, the stems and things, or whatever those byproducts. Can't they just be mixed back in with this stuff
Sure.
to improve, you know, people
Sure,
that turn
that
leaves and
certainly
stuff
would be-
into their garden?
That certainly would be the approach. You don't necessarily have to do that. And some of the things that, you know, you can use the basic lunar regolith itself, or you can add organics, and you can also take other materials that would be derived or engineered from lunar materials. We can go to the next overlay. One of the things that we're missing is volatiles on the roof, and so you can see that there are very small quantities of hydrogen, carbon, nitrogen, and sulfur. Now, from the standpoint of energy production, Dr. Polchinski has proposed getting helium-3, which is another implanted volatile, and extracting that by heating the lunar regolith. And if we heat the lunar regolith to 600 or 700 degrees, then we also drive off these other subsidiary volatiles, which we need for an atmosphere. And so we do have some sources that are available. If we buy Dr. Polchinski's helium-3 proposal, we get carbon, hydrogen, and nitrogen from the lunar regolith. The lunar rock is about 40 to 45% by weight oxygen, but it's all locked up in different minerals. We go to the next slide. Now, one of the things that the lunar regolith, that can be produced there are zeolites. And zeolites have a large cation exchange capacity, and that is important in terms of plant nutrition. So we can derive an excellent substrate for plant growth by manufacturing zeolites from some of the lunar materials.
There's an awful lot of water precipitation. That's where is that why you need the volatiles in the first place? Just use this or whatever.
Well, this is one of the focuses for research at Johnson Space Center, is looking at zeolites as a particular option in deriving acceptable growth moving from lunar materials. As you feed a crew, of course, you have a continual and daily resupply of fresh organics. And in fact, the physical chemical systems have to process and deal with that and recycle that. Of course, that's also what in agricultural and what soils do for us here on Earth. The relative efficiencies and throughputs and the scales of that are obviously not favorable for early stage colonization, but that's in fact what makes planet Earth work. So there's no question that can be done. But then you're also looking at pathogens and processing. Milwaukee since 1906 has been taking products out of its sewers and producing a fertilizer called milorganite. And that had kind of interesting history because Milwaukee was also doing lots of metal productions, and so they had lots of very high levels of cadmium in the milorganite. So for food production, it's primarily for golf courses and lawns. And there was a big scare back, I think, in the late 50s and 60s about milorganite, and there was some thought that ball players were getting it. Lou Gehrig's disease. We're speculating that this might have been caused by the heavy metal in the playing fields that the ball players were on, and so there was a big scare about milorganite. As it turns out, the lunar regolith also has some heavy metal concentrations. It has higher nickel and cobalt in it. And one of the things I think is interesting, just in terms of the kinds of research, one of the problems we have is to learn to grow things with the lunar materials that are there that we can derive from. So we need to find out how to engineer the soils and to grow the variety of plants that we need. On the other hand, I think it's a two-way equation. And this is another area for research, is we can engineer the soils by using various kinds of plants. And so the biodiversity that we have can be used perhaps as a tool for separating out different kinds of toxics or being sensitive to different kinds of toxics. The Wisconsin FAST plants that I mentioned are now being looked at by the EPA laboratories because they're very sensitive to certain kinds of toxic chemicals. And so you can use that plant as a barometer for the presence. You can sow those FAST plants over an area, and by looking at the FAST plants, tell if certain kinds of components are in, because we can recognize that from how the plants react. So there's a whole area, I think, of research that can be opened up to people, looking at the processing of lunar simulants anyway, and looking at how those plants would potentially extract things like nickel and chromium, or possibly ignore it and leave that so it wouldn't be in the food chain. But there are obviously obvious tie-ins between that kind of question and practical issues of looking at processing of soil and using plants to detoxify soils with life. So there's some spin-off applications that come to mind. Okay. This basically is a little bit further diagram of how zeolites would be involved in nutrient uptake by plants. Apatite is another mineral that's found on the lunar surface that would be available as a source of plant nutrients. Some of the micronutrients would have to continue to be earth imported, but we're not talking about, these are very small weights in terms of the amount to deal with, they don't really pose a significant barrier. Much of what we need is basically there. Now, there's not a tremendous focus on this. I mean, there are several different projects that NASA is funding right now. But given the complexity, given the range of food plants that we need to grow, given the diversity of different kinds of soils based on our extensive set of samples from Apollo, we need to know a lot more. We need to have a lot more people interested. And we need to start building and trying to develop these kinds of systems, I think, at a much greater scale than we're doing. We've been to the moon, we've built rockets, we've gotten there and back. What we haven't built is a sustainable biosphere that can produce a reasonable supply of food and use it from lunar materials or materials that are as close as we can make as analogs to the lunar surface. So that's really the purpose. I just tried to sketch out for you some of the developmental issues that we see in lunar agricultural development. There's an excellent volume. I am, by the way, not a plant scientist. I'm a layman and a member of the National Space Society chapter in Milwaukee. And it was our concern to develop an educational program and project that would basically interest students in these things. Many materials that I have here have come out of the Space Lunar-Based Agriculture, which is put out by the Soil Science Society and Crop Science Society and the American Society of Agronomy. This was a 1989 publication. And this has a very extensive bibliography. What I think is very interesting, and you can go through that particular volume, is how many research issues are basically wide open. So this is an area that if you're looking at a science career, if you're looking at space development, a lot more needs to be done. A lot more people need to become interested. And manpower in the pipeline is not a minor issue in terms of all the other things that we hope to derive from space. And that was basically our goal in trying to develop some experiments and some information to involve kids in these kinds of issues. And one other issue is the pressure environment in an enclosed lunar base is not necessarily going to be Earth normal, and people are saying that they would probably operate at significantly less pressure. Well, there's a whole area of work, that we basically also need to see how in fact will that affect a practical working module. We need to have a lot more test beds, in my opinion, to take a look at variabilities such as lighting, pressure. There's some recent, some of the earlier projections, if we crank up the CO2 levels in these modules, that the productivity of the plants will grow. And that is, more recent research shows that isn't necessarily the case. And then indeed, we don't seem to get automatic, it's not a simple matter. If you just pump up the CO2, you're going to have heightened plant growth and productivity. And that was one of the things that seemed to be a very attractive kind of option. Even to do that would be difficult, because while your crew is continually supplying more CO2 from respiration, if you have a plant chamber, you're still going to have equipment which you weight to concentrate that gas and produce it in the plant chamber at a higher level than it's produced in the crew quarters, so that you have in fact a higher CO2 kind of atmosphere. So that isn't necessarily inexpensive to do, nor is it necessarily very productive in production. The area of lunar soil evolution is really what we're trying to get at, and these samples are things. So this is fairly expensive material. The glassy material, which is the stuff that's very dark, is about 10 cents a gram. And so, to have a pound of glassy material and a can of the other particles of rock at 10 to 30% ratio is going to take probably $70 to $100. And what you get is a small pot full of soil. So what, as a teacher or in a classroom, we had hoped to design experiments that teachers could undertake or students for $100 or less. Now the yield of scientific information from these classroom experiments is not something that I think would stand a lot of rigor, because you don't have a lot of statistical controls, you don't have a controlled environment for one school, and
I'm here for the
all
next
those kinds of things really introduce some of the variables. Unless you had hundreds of people replicating the kind of experiment, some of that noise might cancel and you might find some patterns there. So our primary intent of this is not really to pretend that we're professional plant scientists or that students could perform very rigorous research, but we do want to expose kids to a variety of these kinds of scientific issues and to let them plot out what the impact would be of altering the photochrome plant. That's another area that holds some very interesting promise in terms of applied application. The problem with plant lighting is not a minor one. And to take the incandescent lamps or fluorescent lamps up to the moon, you have a lot of vibration in rockets, and your breakage would be high. And if they break or burn out on the lunar surface, it's not easy or convenient to go back and get another light bulb. Exactly.
So most of the weight on the light bulb is the envelope that encloses the vacuum. You've already got that. So what you really need to take is a bunch of tons of filaments and make your own bottles or whatever.
Well, one of the things that's going on at the University of Wisconsin is to use light-emitting solid-state devices. And they're using light-emitting diodes. Those are the ones that produce light in the infrared range. I think are gallium and arsenide. They produce sufficient intensity. There are others that use silicon carbon, and they don't produce sufficient intensity for plant lighting, but they do produce light farther down in the spectrum in the blue-green area. Plants have a variety of different photoactive pigments, and chlorophyll, for example, has a couple of variants. There's chlorophyll A and chlorophyll B. Chlorophyll A operates, it receives light at about 750 nanometers, and I think chlorophyll B at 763. And those two forms kind of exchange if one flips into the other. And so you have the ability to tune your light output very specifically to those, instead of having to have light generating across a whole range of frequencies. And you can just power a very narrow spectrum output, and potentially you can give the chlorophyll the energy that it needs without a lot of extraneous. And so that's one of the areas that may also address some of the energy requirements. Another interesting thing that is being looked at again is pulsing the lights. Chlorophyll apparently will take anywhere from 40 to 400 milliseconds to absorb photons of light and then pass that light energy down streaming in the photochemical reactions of the plant. So, if it's accepted a proton and then it's carrying that proton down the chemical pathway, while it's filled, either if you shine light on the chlorophyll, it has no impact. If you can pulse the light, potentially you could also save a significant amount.
Well, there's a certain limit for intensity level. I'll be honest, you just overheat the plant, it can't absorb beyond a certain point.
Sure.
So you would flash it, hopefully something less than that, just for near that level, and then let it shut it off or throw it on another plant. You could use, say, a rotating mirror and just one light source for several plants.
Sure.
Could you use natural sunlight to some extent?
Well, the sunlight intensity is very, very high on the lunar surface, and that might, if you just used some sort of reflector mirror system to bring your light underground or into your plant shelters, I don't know if you can really.
You can diffuse it to some extent.
Fiber optics. Yeah, those would be.
Fiber optics, or even just a bar of clear glass, which would be a giant fiber, in fact, long enough to reach out. You could bring it in and then the lens diffuse it, so you can get the intensity out of it.
Well, some of the work on there are an array of different photochemicals. There's phytochrome, which has a lot to do with controlling plant development physiology. There's chlorophyll. There's several others, and the other molecules operate at lower levels in the spectrum, and that's where we don't have a solid state ability to tune, produce light at the intensity required. But there's a whole of work that needs to be done there in looking at, what range and what intensities, what's the ratio for those various photochemicals, and that's something also that needs to be done. So we're just looking at a lot of those issues. So being able to produce the lighting technology that's going to be reliable, and, if it can be lunar source, that's great. The LEDs, for example, right now it's about, to get the small one is about $404.50, and to put a 2-foot by 6-foot grid together is $5,000 to $6,000. The WIXR, which is the Wisconsin Center for Space Automation and Robotics, I think I have a brochure. There's has this, so for our purposes in the classroom, this is out of the question. But one of the things we are trying to look at is that can we put some filters together so that we could, in essence, use a regular spotlight and filter that and get a much more narrow focus of different output. And so,
Could you, like I said, could you use daylight to filter the stuff?
Yeah.
So that you wouldn't need to, for your experiments, anyway, you wouldn't need to do anything but to filter over, say, the window. And then,
Sure.
And do the lights, say, red, green, blue, whatever.
and that's what we're trying to do now, is we're trying to I'm just working with a lighting engineer and trying to develop some filters that also would allow students to build some devices that would allow them to filter out certain frequencies of light and conduct simple experiments of that sort. So these are some of the issues that we started with, we thought would be interesting to involve students in, and that's what Lunar is all about. We have two different experiments here right now we've designed. One was the lunar photo period, and we call it the lunar dark hardiness experiment. The second is the lunar soil evolution experiment. And Dr. Bill Easterwood was at the University of Florida. He's now the national grounding manager for a large fertilizer company. But he had conducted research on soybean and wheats using this lunar simulant material. And one of the interesting things he found is that over 8 crop cycles, this simulant, which has a pH level of 8, dropped to about 6.4. The wheat that he grew over 8 crop cycles dropped it to about 7.3. The speed at which you can modify the soils and the root acids basically changed the lunar simulant material.
That be taking nutrients out of it or whatever.
No, the acid exudates from the roots basically changed the pH of the soil. And it also changed the mineralogy, so it made it more into a cement-type clay material. And that's what I was talking about before, is learning how to re-engineer the soils of the plants. There's a You know, he's the only guy who's
Doing
tried to do
something
that.
on their own.
Yeah, yeah. I guess we're at
Yeah,
time.
yeah, we gotta move.
Okay.